statistical data privacy, quantitative methods in the social sciences, and social values in data governance. His work spans multiple disciplines with publications, invited presentations, and collaborations in statistics, machine learning, social sciences, and law. He's the recipient of the US Census Bureau Dissertation Fellowship and the ASA Pride Fellowship. Prior to joining UMich, Jeremy completed his PhD in statistics at Penn State and his BS in physics and MS in statistics at the University of Chicago, where he's a research fellow at the Center for Data Sciences and Public Policy. We're very excited to hear from him today, so thank you, Jeremy. Leaving this.
Okay, hi everyone. Can folks hear me? Hi everybody. My name is Jeremy. So I am filling in at the last minute for my previous advisor, Sasha Slakovich, who unfortunately could not be here at TPDP. I will be giving a similar talk based on some of the themes that she was planning to present on her work, but there are some things that I'm going to do to make it a little bit more applicable for this audience. So at a high level, this is just a talk that I'm going to focus on a non-technical sort of interface between statistics and computer science aspects of differential privacy, focusing primarily on the utility side, thinking about uncertainty quantification, the different ways in which we talk about uncertainty quantification, and what that means for better unifying these different approaches. So I'm going to be focusing on primarily inference problems from public use data, and these are the problems that tend to impact social scientists working with DP outputs the most. So I'm not going to be talking about other things in terms of privacy models or interpretations or settings where these statistics are really only used internally. And I've gotten to work with a lot of great people, such as at Tumult Labs, one of the sponsors, at Norfolk U Chicago, and at Census, but I'm speaking just on behalf of myself today. So the reason I think it's important for us to get thinking about these problems is that there's a bit of a divide between the statistics approaches to data privacy and the computer science approaches to data privacy. And there are a lot of sort of structural reasons why we don't engage with these two literatures as much as we might like. Oftentimes, we're not disseminating this work to the same audiences. The definitions and problem assumptions and the kinds of solutions that we like or don't like tend to be different across different outlets. And in general, it means that when I'm in a situation where I'm reviewing stats papers, there's usually not enough engagement with existing CS literature or vice versa. And as someone who is a statistician by training who works in this field, I want to make sure that these two fields are talking to each other. And what we see here on the right is a citation network going from the original Dwork et al. 2006 paper for the Sweeney paper 2002 in K-anonymity, and we see that this was sort of a cleaving point at which the citation network sort of break off into these two groups. And what I'm trying to do is make sure that these two groups are ultimately working together. And I think uncertainty quantification is one of the ways that we can start to do that. So at a high level, I want to talk about three main points. The first one being that this kind of work is something that has a bit of a statistical history and lineage. But again, this is something that Sesha would be more qualified to speak on. I won't be able to go to the details here. Where I think there are more opportunities for us all to work together are specifically in issues related to end-to-end uncertainty quantification. And this is where I think CS and statistics have the most influence on one another, and specifically the places where it's the kind of influence that often goes underseen or not as represented in the kinds of literature that we talk about here. And thinking about ways in which we can infrastructurally make this coupling tighter. So in order to get more statistics people exposed to the ideas that this community generates, Sesha and I wrote a review paper last year that focuses on teaching more statisticians about the concepts of differential privacy. Because in a lot of places, statistical disclosure control or traditional methods that are not necessarily going to have formal guarantees are still the norm. And a lot of the people in our field don't really have exposure to the kinds of things that we all talk about on a regular basis. So what we were trying to do is really try to say, here are the great things that differential privacy offers and bring it back to our community. But what we realized is that a lot of the core problems in terms of just how we reason and communicate about disclosure risks and the ways in which we actually quantify the uncertainty that comes through them haven't really changed, even though differential privacy has given us this really rich literature to help navigate that trade-off. And even though in this particular space of people, using this privacy model as sort of a non-starter, it is the starter, is something we're all comfortable with. In other places, it might not necessarily be that case. And these are the places where these translational issues tend to be quite difficult. And just this is probably the only slide I'm really going to talk about history, is that despite the fact that the formal language that we use for thinking about these kinds of issues is really new and modern and rich, the general ideas of injecting noise into data as a way of masking confidentiality and the idea of correcting inferences from noisy data have been around for a very, very long time. Randomized response dates back to the 1960s, and looking at errors in variable models, this dates back even to like the 1940s. Now, obviously, we've gone a lot farther on both the privacy side and the utility side, and this is great, but these have a lineage and there's something that we can really be doing to connecting them. And what really got me as a quantitative social scientist excited about differential privacy is the way in which we can leverage transparency for valid statistical inference. So anytime we apply any technique to decide whether or not to release a statistic, we are changing the distribution of the thing that we are releasing. And traditionally, these were interventions that were done in secret or behind closed doors in ways that we couldn't actually show how that affected inference. So we often talk about the privacy concerns from k-anonymity, but there are also lots of utility concerns for k-anonymity. Conditioning on k-anonymity results is going to invalidate a lot of inferences. And these are things that we really should be thinking about. And the whole reason that we have methodological transparency in DP is that we can enable this end-to-end uncertainty quantification. And it's also something that we use rhetorically when we're talking to people who might use this technology. We sort of paint this story that we have over here on the left from Ted's blog that I'm using this picture. We have some inherent uncertainty in this data that we are constructing or collecting some statistic on. And we hope to be able to say that when we introduce some additional noise due to DP, it's going to be generally smaller relative to the errors that we think to some degree exist in the process. And this is a story that's very frequently used to convince people that they should use this technology because we're not going to affect inference too much and we'll be able to do something a little bit better in terms of giving this data some privacy protection and instilling some social value. But this picture here is a story, and we don't always do enough to interrogate the story or make sure that the story is true. So this story is really only applicable if we make a very particular set of data generating assumptions, and whether or not we actually choose to work with those data generating assumptions or accept them, that will determine sort of the relative noise that we might have on the left versus the right here. Additionally, the kinds of queries and the kinds of privacy loss that we assign to those queries is a decision-making process that we ultimately might think is going to affect whether or not this is going to be true or not for certain classes of models or others. And the other sort of deeply ironic thing about this is there are cases where with probability 1, we can't satisfy this and simultaneously satisfy DP. Because if we say that this is always true, we might unintentionally be revealing something about the database. So not only are these questions of validity and decision-making, potentially endemic to how we talk about uncertainty, it's also something where DP itself might be the thing that gets in the way. And then there's the broader concern of, do we always want this to happen? If DP is going to disable a particular inference from happening, that might not necessarily be a bad thing. Maybe it's an inference that could only be possible with revealing some personal information that we want to protect. So it's not always that this story is necessarily what we might normatively desire, or we might question who gets to make these decisions. And as we've seen from the real world deployments of DP, doing this in practice is really, really hard because end-to-end social science uncertainty quantification deals with human data that is really messy and gross. And if we start to unpack what uncertainty quantification is, we can start thinking about this at a higher level. And the main reason I am concerned about this is because we are publishing thousands and thousands of papers on methodology, and we don't have enough visibility into how these technologies are being used in practice in social sciences. And of these deployments, there's even less work on the ability to actually think about what this uncertainty quantification means in an end-to-end basis. Now, if you are someone for which this isn't a problem, then the rest of the talk is going to be probably irrelevant for you. But I hope that by the end of this, I can at least convince you that we can do a lot more to try and close this gap. So in order to do this, I want to start by trying to sort of productively complicate the way that we think about uncertainty quantification in this picture. So the traditional way in which we talk about DP, we have some perfect little tabular database. We have our DP query system, and we have what I can only presume is an evil statistician and who's trying to do something horrible, like learn something about a parameter. And we have this nice model where we ask questions, we get the answers with DP, everything is great. And buried in this is not only an assumption about the mechanism for which we respond to answers, but also something about where this data came from. We are assuming something about a parameter, theta, something that we're trying to learn about the world, something that using some class of models, we could be extremely generic or extremely specific, tells us something about some data, and we have some output that we've done something to where we know the exact distribution. And our goal is to use Y to infer theta and not use Y to infer X. So it's the difference between a probabilistic graphic model where we're going 2 up the chain versus 1 up the chain. But if we look at what these look like, even zoomed out a little more, we see that there's a lot of complexity in deciding how to model human social science data and how to model the actual privacy side. Now, thankfully, the transition between X and Y is the thing that most people in this room are already familiar with, so I don't need to spend a lot of time on that. But human data, especially in the social sciences, is really, really messy. It's almost never IID. There's almost always structural errors. And usually those are either going to induce dependencies between records, give us different distributions for records, and lots of social science work, including the issues with replicability and reproducibility, come from differences between what we're trying to infer about some population, who we actually collect data on, what we're trying to do in terms of the thing we're trying to measure versus what we actually measure. Now, the specifics of this flowchart, I'm not going to go into for the interest of time, but the general problem is that we're masking a lot of complexity on the modeling side that even before we use DP. And then once we get some DP statistics, we're not necessarily going to exclusively use these in practice. We're going to be pulling from other data sources. We're going to be pulling from knowledge that we might have about similar data or relationships between these data sets. Like, these are the standard practices that are used in almost all empirical social science research. And even this presumes one particular kind of data generating process. So we can zoom out even more, unfortunately, and get to this place where we're really starting to see the modern problems of statistics. How do we decide between different mechanisms? How do we decide between different data generating processes? How do we integrate data where we know that these things are coming from different processes and define different populations? And all of this happens variably in time and variably in these human decisions. We focus a lot on things like composition and activity, but these also affect the way in which we are defining inferences and how the choice from one part of a data making process affects something else later on. And it's not just at the level of models, it's at the level of the privacy mechanisms, which we study in composition, and the levels of the actual way that we make decisions. So we went really far from this to this. And I think the big problem here is when we talk about uncertainty quantification, we tend to talk about it in a very, very narrow way, but there's a lot of different things going on here. And we might care about one part of it, or we might care about all of it. And we should at least have a shared language to be able to talk about these differences. So when we're thinking about what it means to account for errors, we're often talking about a few different things. Sometimes we're talking about something that is a pure function of the data. Say, for example, if we have some statistic that we're computing on it, how close is what we're going to release with DP to that statistic? But then we can start to think about different ways of doing this when we entangle the thing that we're trying to estimate with the mechanism itself. So we could ask questions about if the thing that I'm trying to estimate is a function of some statistic that is changing, then we can think about how that estimator process is going to change if we input a DP versus a non-DP statistic. There's also questions of when we assume something about a so-called true value from a data generating process, what is the difference between what we're actually trying to estimate with DP versus this ground truth? And then we also have a differences in differences problem where we're thinking about how close is the distance between the ground truth and the DP estimator versus the ground truth and the non-DP estimator. And one of the I think the difficult communication problems between stat and CS is we tend to only think about one of these and then make modeling assumptions so that they all look the same. And that might not always be true. Like, for example, for exponential family models, which we all at least have some vague familiarity with, you can define some ways of exchanging between these kinds of conditions. But in general, you can't always do that. What might work for one might not work for two or three. And this is something where pulling in those modeling assumptions and thinking about how they affect end-to-end uncertainty quantification can be really helpful. Additionally, we have different kinds of model spaces that we consider, and the kinds of assumptions that we make in terms of making them more generic or more specific are interacting with like different forms of knowledge. And these different forms of knowledge are things that sometimes we feel comfortable about, sometimes we don't feel comfortable about. In general, in DP, we're in a setting where we are trying to explicitly characterize a distribution that we know and understand. And that makes us feel comfortable because there is no model misspecification problem. We know exactly what we are doing to the data, we know the distribution, and we feel comfortable undoing it because it's correctly specified. However, making like unverifiable assumptions for the rest of it is the entry ticket that we have to pay to do inference. We can't do inference if we don't make data generating assumptions in the broader sense. We can only characterize these known distributions in the DP case because we are explicitly modeling the intervention that we care about. And the kinds of modeling assumptions that we make can sometimes be productive in terms of helping us improve our understanding of uncertainty and be more conservative. So if we know that data is imperfect, which we typically know for social science data, then we can do things like modeling missing data, modeling measurement error, modeling the grossness of the data making process in a way that is productive, versus these more unverifiable phenomenological assumptions that we are going to be leaps of faith no matter what. Like assuming that data is exchangeable, assuming that distribution lives in a particular functional space. These are things that are difficult or in many cases near impossible to verify. But these are, again, the price of admission for doing statistical inference. And then there are the actual things that we're trying to do when we're actually characterizing the different kinds of uncertainty that we're quantifying. So we're most used to thinking about the distribution of some non-private output given some private output because this is the thing that we focus on in DP. We focus on the mechanism and how we can effectively design it. When we start to add in the broader data generating process, we are entangling the mechanism with any of these assumptions that we put in. And there are lots of different ways of doing this, particularly when it comes to trying to measure these different distances that we care about. Now, we know that these are all going to have some sort of concentration behavior. So we all, at the end of the day, want these to concentrate around the thing that we care about, usually a non-private statistic or a non-private estimator or some true population parameter. And concentration inequalities are the traditional way we do this, where we have some asymptotic sample complexity on the upper bound and lower bound. We want them to match, and that gives us a good sense that we're doing this effectively. We could be We could say something weaker, such as like an asymptotic result about a distribution. We could say something more precise, such as characterizing this distribution exactly. But there's multiple ways of doing this. So between the different targets, the different sources, and the different tasks, we've created this weird constellation of all of these different things that we call uncertainty quantification. And it's only under certain settings that we can really exchange information between the two. And it sort of created these two different modeling cultures around the way that we think about uncertainty quantification. So we have a tendency, I think in general, both in stat and CS, this is all of us, to want to focus on narrower problems with fewer assumptions. And these are the settings where, like a lot of the work that we've seen today, we're thinking about matching upper and lower bounds. This kind of work also shows up in statistics through things like conformal prediction or finite sample inference under exchangeability conditions. These are the settings where we want to be as narrow as possible, model something that we really characterize as much as precisely as possible, and we want to be as generic about all the other assumptions. Whereas in applied statistics and the quantitative social science, we are trying to learn something about a population where we know we don't have good data, where we're trying to deal with the messiness and we're trying to think about things in a more end-to-end setting. And this is where we really have to treat the data that we don't have, the confidential data, as missing. And this gives us all of the different tools that we have to work with this, including like semi-parametrics or Bayesian computation, any approach that allows us in some internal sampling mechanism to impute the things that we don't have. Now, this group on the left, this is our comfort zone. This is where the majority of the work that this group does sits. And there's nothing inherently good or bad about either approach. We need both for research. And I'm not trying to suggest that one is better than the other. They're just different and arguably complementary in some ways and contradictory in others. But the things that tend to motivate this are some of like the design principles that cause us to want to be in our comfort zone. Ideally, because we think of these systems as being interchangeable, we want to be able to swap one mechanism for another. We want to be able to swap one parameter estimation for another. We try to design things in a modular way. We try to isolate one part of the system and think about optimizing that one part of the system to get the best possible estimator for a particular problem. Additionally, because differential privacy is about mechanism design, we are fundamentally interested in systems that we can control. If we're in a setting where there's a lot of garbage happening before the system starts and after the system ends, we want to focus narrowly on the things that are an intervention that we're controlling. So if we can decide the mechanism, that gives us a little bit more faith in sort of the integrity of what we're doing. And from the generality perspective, in order to make broader claims about the efficacy and applicability of this work, we are going to generally want to prioritize fewer assumptions. And both the blessing and the curse of this approach is that a lot of these properties that we use in mechanism design don't necessarily transfer over to statistical inference. And this ends up being, I think, the pain point between our disciplines, where we can design modular systems. Statistical inferences are not modular. You can't modify one part of that pipeline and expect everything else to work as expected. And from the control perspective, oftentimes social scientists are working in cases where we don't actually interact with query systems, where we have the full freedom to define the things that we need. We don't get bespoke solutions for everything. And what's optimal in one setting is not necessarily going to be optimal in another setting. And when it comes to generality, the kinds of assumptions that get normatively accepted in any group are by construction always going to be over-inclusive for some and under-inclusive for others. So there are lots of data generating assumptions that are less generic and maybe more restrictive than the sort of standard exchangeability setting. But in those settings, we might get better finite sample guarantees. We might get constants that we can work with to get some tenable, provable results. Alternatively, there's lots of social science data that isn't IID. There's lots of social science data where we need to think beyond these sort of traditional framings. And it's not that this is like a good or a bad problem, it's that this is the thing that we're still trying to come back to. We have so many different methods and so many different ways of building up these individual components, and we don't have enough visibility into how all of these components are glued together. And the things that we prioritize in terms of optimizing these individual components are completely unintentionally making it harder for us to glue things together. And this isn't necessarily a good or a bad thing. This is just like a difference in the expectation between the way that we think these fields should operate and the way that they do in practice. So when we optimize these individual components, what we're effectively doing is we're saying, as long as I like build the best mechanism in this one particular setting, I can modularly input it into some broader system, and the problems affecting inferences in terms of how you actually construct the data or how you do inference on it afterwards are going to be someone else's problem. We can defer that to the statistician before or after this wall. And because of thinking back to those sort of flowcharts that I was showing you earlier, we're creating bottlenecks where even if we don't necessarily choose to do so, we're restricting the space of models we're considering. We're restricting the spaces of statistics we're considering. And if we don't think about designing some of these parts together, we're not going to be able to close this gap between theory and practice. And there are sort of two broad approaches that I think would be productive for doing this, because it's not to say that modularity itself is bad. Modularity is still a good design principle and we shouldn't abandon it. The question is, we just need to, as DP is transitioning from a theoretical tool into something practical, we need to decide where we want this modularity at the intersection of stat and CS versus where we might want it more broadly, less broadly, and require bespoke solutions. And this is a problem that is not specific to privacy. It's not specific to any data-driven technology. So Deirdre Mulligan and Helen Lissenbaum have some work on what they call a handoff model, which is this idea that when you are building a modular system, if you assume that its modularity isn't something that's going to change, if the modularity, I'm tripping over myself here. I'm completely blanking. If you are assuming a system is modular when it is not, inserting one component and replacing with another is going to affect components that are outside your field of view. And what I think we can do is either build components that widen the field of view or decide where we need to build something bespoke. And to give some sort of high-level ideas about ways we can make this concrete is there are lots of problems that are sort of in the background of a lot of the work that shows up at conferences like TPDP that could be really helpful for what these sorts of like modularity settings are. So when it comes to thinking about the way we evaluate the success of a particular tool, we often tend to think about it explicitly in sort of the narrow sense, in terms of, can we get an upper bound, lower bound, call it a day? And we have all of these connections that we're establishing between DP and statistics already. We know that it is possible to do end-to-end inferences where we do model checks, where we do all of the kinds of uncertainty quantification that we care about, but we're not actually like thinking about the ways in which pulling off one part of this process is going to affect the other parts of this process. We've also seen lots of great talks about the connections between DP robustness, stability, and replicability. And yes, we have all these great algorithmic definitions. There's also all these opportunities that we have to say, what does that actually mean for how we intervene in these systems? Does it mean that we use DP to create replicable algorithms? Does it mean that we start at a different place and find an optimal conversion? Like, there are existing literatures on all of these different topics. And while the formal connections are nice, it would be nice to see what that's actually going to do to affect practice. and particularly how these different kinds of formal translations turn into translations of decisions that actual people make when they use these systems. There's also lots of work on that we still need to do when it comes to regime detection or like hyperparameter tuning. And I don't think that I need to go into too much detail about this, but oftentimes when we're looking at things purely from the sample complexity framework, we are quick to make the assumptions necessary to establish these different regimes. But when people are deciding what mechanisms to use, they need the ability to be able to make that decision concretely. And being able to surface that information is going to be really important if we want people to use this. And there's also lots of problems that I don't have time to go into at the high level when it comes to directions for these more bespoke analyses. And I've been referring to DP this whole time as one sort of unified framework, but this systemization of knowledge paper by Ted and a friend, this shows that there are hundreds and hundreds of definitions of DP. And one of the big problems is that they don't all share the same principles. They don't all have the same formal analyses, and they all have different implications, both on the privacy side and in terms of how we're actually going to map these onto the different assumptions. And right now, even though we have all these definitions, we're not necessarily tailoring them to all these different use cases. And because, as we heard in the panel yesterday, like the ethical and legal side of privacy is really, really complex, we might need to think about some of the ways in which some of these variants could be useful or not useful. And there's lots of work that we can do infrastructurally to start to support these kinds of things. NIST has done a great job thinking about new kinds of benchmarks that help drive DP from this theoretical tool of analysis into something that is end-to-end practical. And the kinds of connections that we've already talked about imply very natural benchmarks. For example, we talk a lot about differential privacy having connections to replicability and the kinds of issues that make social science problematic in the first place. One of the natural benchmarks could be pick a paper that you see from American Journal of Political Science and replicate it end-to-end using DP. I would love to see examples of this as a benchmark that is not necessarily going to satisfy the kinds of algorithmic properties that we like, but it will demonstrate a buy-in that we can get people to use DP at a high level in the first place. So I know that this is very different from the way that we traditionally think about problems. This is trying to bridge a translational gap that is usually something that slips through the cracks in academia, and it's something that we might not always necessarily value for all the same reasons, because we're coming from different fields and we're trying to learn different things. And it reminds me a little bit about why I named this talk Method and Mess, is because of this quote by John Law, who is a qualitative social scientist who works on issues in how people use social science methods in practice. And he has this beautiful quote where he says, "What happens when social science tries to describe things that are complex, diffuse, and messy? It tends to make a mess of it, because simple, clear descriptions don't work if what they are describing is not coherent. The very attempt to be clear can simply increase the mess. And we should imagine what it might be to remake social science in ways better equipped to deal with mess." Sometimes when we're in algorithmic learning theory land, we forget that we are operating as social scientists. We are making assumptions about the way that computer systems are configuring relationships between people. And relationships between people are just inherently gross. And at a high level, we have to make a trade-off between the kinds of places where we can work together to build modular tools, or the kinds of places where we need to tailor systems to the complexities of modern social science. And these aren't easy problems. These are very difficult problems. These are the foundational problems that want us to continue to get social science data curators to use DP in the first place. Because DP is still a great technology, and we should continue studying it because these are the things that we can solve with it. It's just that we're in this translational phase where thinking about uncertainty quantification end to end is going to buy us a lot more than we think in terms of both the methods and the mess. And that is the end of my time. I am available during the poster session you can email me. I got very, very last minute feedback from Session and Dragestry, so thanks so much for them on that. A couple personal references, happy to provide any other references upon request. And that should give us about like 5 minutes for questions. Thank you.
So you have time for questions for Jeremy? I have a question. So you talked a lot about how complicated social science can be and modeling things, and it seems like a problem that happens independent of privacy. Do you think there are fundamentally different challenges with DP, or like we're just a younger field that hasn't developed the tools that traditional statistics have?
Sure. So I think it's a difficult problem to answer because of these ways in which, like.
Actually, sorry, can you repeat the question?
Oh yes. So for the folks who are on Zoom, Audra asked a question about to what degree the problems that I am talking about are independent to social science, or are they independent to privacy? And this is effectively the tension that I am trying to talk about, which is that the way that we frame these individual problems allows us to isolate what we think are the privacy components when really we are unintentionally impacting the way that people do social science. And this is something that is usually intentionally abstracted away so that we can design systems in a way that gives us that control. And the difficult translational problem is not just one about the different and technical approaches, it's also the differences in how we should feel accountable to different parts of the system. It's something where we're not used to thinking about things that we can't control for people who we don't necessarily see as part of our picture, but that's where moving from the sort of individual component optimization to the systems level thinking can get a little bit more flexibility in how we solve these problems.
Great job, Jeremy. Really enjoyed it. So I have a question. So you talked about how to uncertainty quantification, the right way to do something like that. How can different societies be replacing existing privacy methodology? So is there like a literature that we should be looking at that uncertainty quantification understood with the current privacy use and translate that over to different privacy? Or do you think like it's a new problem that comes up with different privacy that doesn't exist with?
Yeah, so that's a great question, and I will repeat that for everyone here. The question is there a literature that does this comparison between like traditional statistical disclosure limitation, uncertainty quantification, and what we give a DP? And one of the big structural reasons why this literature hasn't existed is because traditional methods rely primarily on security by obscurity. You don't have methodological transparency in comparing current methods to past methods. And this has been one of the major pain points, say, with the Census Bureau's implementation, where the things that they want to say about their old methodology are things that they are required not to be able to say things about. And it also is a thing that affects uncertainty quantification. There are certain parts of that end-to-end pipeline where they can't say something about how many people they're imputing or the non-response rates in certain like small geographies, even though these are the problems that organizations deal with internally. So it's one thing to presume that we have control over the system or even visibility. But the reason that literature doesn't exist is often because these policy alternatives are hidden from us. We don't have visibility into be able to do these apples to apples comparisons. And this is the real pain point for communicating about uncertainty, what makes it quite difficult.
I think a question that lies slightly in between both of them, but maybe not stated here. So looking at diverse populations, where you may have a large group of the population that has basically one type of distribution and a smaller group of the population that has a different type of distribution, and thus appears to be outliers according to traditional privacy techniques and is more susceptible to noise, different privacy. Can you talk a little bit about, is that in the overlap of things that are messy for social science, even if we didn't care about privacy, things that cause uncertainty for our results on traditional methods, and things we have to pay attention to current methods? And also, if anybody wants to try their own techniques out in this circumstance, please check out the NIST diversity here.
Great, so I will repeat that question for Zoom. So the general question is, how does this interplay between these two fields affect specifically equity issues related to like parity when it comes to different diverse populations? And I would say that a lot of these problems, I think, are just endemic to doing any disclosure avoidance technique. Like these were issues back when traditional disclosure limitation issues were still like sort of the de facto norm in a lot of these agencies. And that problem doesn't necessarily go away with differential privacy. It just gives us more visibility into a problem that was always there. And this is why that visibility is really important, because it's difficult to try and diagnose all of the reasons why lots of social science based on public data isn't reproducible. But by making part of that process visible and exactly specified, we'll get closer. But it doesn't solve the underlying equity issue just because that is endemic to the whole process. And it's not just that for different groups, the privacy calculus and the utility calculus differ. It's that you have different trade-offs and different social relations between who's collecting the data and their relationship to what they expect it to do. And it's going to be highly contextual.